Okay, today we're going to look at some miscellaneous review topics, and so that we can, once we get started with new items, then we can proceed fairly quickly. Okay. All right, so the first thing that we're going to review is the topic of indices, also called exponents. All right. If you recall, whenever I have an expression a to the n, we would call this a is called the base, and the n is called the power, exponent, index, or plural is indices. And we had several rules to deal with these. Our base, we're always going to be taking a, well, typically, our a is positive number, and our n could be any real number. All right, now let's look at the rules, or remind ourselves of the rules of indices. We have first rule, the product rule. Product rule, if I had a to the m times a to the n, this was the sum of the index. All right, and we see that this is true. So let's look at nice whole numbers. If I had a cube, so I'll just write out a few of these. A cubed times a squared. Recalled in the initial way that you learned this, the long method, you had 3 copies and 2 copies. But if I multiply them, in all I had 5 copies, a to the 5th. How could I have 3 and 2 and end up with 5? It must be a sum. Right, so that gave us our first rule. We can continue to remember some of our other rules. We had what we call the division rule. Well, let me just unity. A to the first power is just itself. Then let's look at the division or quotient rule. And we had a to the m divided by a to the n, and this was the difference. Again, recall by example. Let's take some simple examples. Sometimes if you forget these rules, you can look back what is a pattern from my simple example. So if I went back to first principle, the numerator a to the 5th is 5 copies of a. The denominator is 3 copies. Using fraction reduction, I would cancel these, and my final answer, a to the 2nd. So what it tells me is that if I have a to the 5 over a cube, I could write this as 5 minus 3, which is exactly what I got here as a squared. Okay. Oops, sorry. Wrote the wrong thing there. I'm doing my corrections. So we can see where that division rule is correct, at least with nice whole number powers. Let's look at some consequences of this. So consequences of our division rule. Let's look at the first consequence. Suppose I have a cubed over itself. Well, what would I get? If I went the long method, then this would be 3 copies of a would be divided by 3 copies of a. I'd end up with 1 over 1, which is 1. And however, based on my division rule, I can see that if I am dividing same exponent, then I must subtract, but this is nothing more than a to the 0. So for some of you who keep writing some new rules out there, please stop, think about it. Whenever you have a to the 0, it is 1. Again, we are assuming that the base is not 0 itself. Alright, so this was nothing more. So this is known as the 0 power rule. Right? And please remember that the 0 power is quite different from the unity power. A to the first is one copy of A. A to the 0 is just a number 1. All right, let's continue with our next rule. Again, it is a consequence of the division rule. So let's start again by example. Last time with the division rule, I looked at a to the 5th over a cubed. This time I'm going to change the order. I'm going to put the smaller power on the numerator, larger power on the denominator. If I go my long way and write this out, then this will reduce, and in reduction I will end up getting 1 in the numerator and a squared on the denominator. However, again, as I did in the previous example, if we look at the division rule, we are supposed to subtract the exponents. I get a to the minus 2. So this has shown me that a to the negative 2, a to the negative 2 is equal to 1 over a squared. We can generalize this idea and write a to the negative n is 1 over a to the n. So this is called the negative power rule. Right. So these were some of the rules that we had, and we can even take this negative power rule a little further. So it's telling me if I have 3 to the minus 2, I can write it as 1 over 3 squared, and of course later on I can simplify that. And but at the same time, if I had something like 1 over 5 to the negative 2, I can also get rid of that negative power in the denominator by bringing it up to the numerator and have negative of negative 2, or simply 5 squared, which is 25. So looking at this negative power rule, if we just spend a little time and look at some examples, if I had x squared, y to the negative 3, and z to the negative 4, I should look at those items that have a negative power, right? So both y and z have negative powers, and what will happen is I will move their relative position. If it's in the numerator with a negative power, we can get a positive power by putting it in the denominator, and vice versa. If, for example, here z is in the denominator, it's to a negative power. If I move it to the numerator, I get the opposite. Some of you don't believe that. Let's look at it from a longer way, or from scratch. But this is the fastest way of, right? So this is the fastest way of getting it all positive powers only. All right. Now, if you don't believe me, let's look at an alternate way. Okay. So anytime we have a fraction, recall that it can be written as a divided by b. And if you remember fractions, we could furthermore write each part a over 1, and the division becomes a multiplication sign, and we take the reciprocal of the second, that part. Okay? So, let's look at the problem at hand. We were given x squared y to the minus 3 over z to the negative 4. Let's write it in the form. Here's the numerator, x squared. I'm just putting it in a bracket because I want to isolate what's happening. And z to the minus 4. Based on my knowledge of negative powers, the first term can be written as x squared over y to the third, and we are dividing by 1 over z to the fourth. Division becomes a multiplication, so I end up with x squared over y cubed. Division becomes multiplication. I take the reciprocal of second fraction. If I now combine this, I end up with exactly what I had. Seems like forever later, right? So we end up with the same answer that we had gotten in just 2 steps by making that connection as to the relative position of the base, and if it's a negative power, what's going on there. All right, so all of those are rules that you have learned already. We have our product rule, unity I just put there so that we'd remember and be able to distinguish it later on from the zero power rule. We had the quotient rule, and as we saw, we have the negative power rule. The final rule that I want to mention before we actually try and do some review question or some more review questions is what we call the, I think that's number 6, is it? Yes. All right, is what we call the power rule. Okay. So what is the power rule? The power rule says if I have a to the m and I raise it to the nth power, this would be a product of the powers. Let's look at it by example. So if I had, say, a cube and a squared, well, using the outer power here first, remember that would mean I need 2 copies of whatever was in the bracket. So it would mean I have a cube times a cube, but then by either if I wrote this out from scratch, 3 copies of a times 3 copies of a, or using the product rule, I would now have 3 plus 3, 6. So I end up with a to the third all squared is a to the 6. The only way that I can get these powers here, 3 and 2, to end up being 6 is that there is a product. So another way of saying this is that in the power rule, the powers multiply all the powers of the terms that's inside the bracket. So let's look at what we call the general power rule. Right? Because you are familiar that if I should have, say, 2x cubed all squared, let's not do 2, let's do a different number. Or let's do 5x cubed all squared. Well, the first thing that we should recognize is that 5 is to the first power. So my solution will be 5x, if I took my time and wrote this out, 5x cubed times 5x cubed for the 2 copies, I ended up with 25 and x to the 6. Could I do this a bit faster? And of course, by now you know that the answer is yes. And so we would take the powers or recognize the power on each term and multiply those powers by what's on the outside. So we're raising each term to that power that's on the outside. So 5 squared, x to the 6. 5 squared is nothing more than 25, x to the 6. So let's write this power rule a bit more generally. And we typically do it in this fashion. A to the p, b to the q, c to the r. If I raise all of that to the nth power, I would have a to the p n, b to the q n over c to the r n. Right? So it doesn't matter what's inside as long as there's either a product, it's a single term, right? All of these items will be raised to the power on the outside. Okay, so hoping that you remember, or this has jogged your memory from the summer, let's look at a few exercises just to ensure that we're on the same page. Okay. So question 1. So let's look at some questions. All right. If we had, say, let's tease you with some fractions, and we are multiplying these things, 16x to the 5th, what do we do? Well, this is simply a multiplication, so we can combine our numbers or rewrite, change the order. X to the 4th times x to the 5th. Regular multiplication of numbers, half of 16 is 8, and then x to the 4 plus 5, which is 8x to the 9th power. So here's my final answer. Let's get a bit more creative than this, and let's look at part B. So 6x cubed to the 2nd power, 2x squared to the 3rd power, and we want to multiply that by We want to multiply that by 3x squared all to the 0th power. Right, so I'm really challenging you here to see if you recognize or remember what's going on. So we're going to follow the order of operations, which is, if we look inside the brackets, nothing can be done. So we look to the exponents or powers and see what we can do. So we're going to use the power rules, going to get rid of these brackets and the powers on the outside. And so what we end up with is 6 to the 2nd power, x to the 6th power, 2 cubed, and x to the 6th power. The term here is raised all to the 0th power, so I really couldn't care less what's inside. It will end up being 1. Recall, whenever we're presenting our answers, please reduce everything to their lowest form. So the x to the 6's cancel out. I can write 6 squared is 36. 2 cubed is 8. Reduce it. So we would have 4 goes into both of these numbers. So we end up with 9 over 2, which is 4.5 or 4.5. As a general rule, we prefer leaving our answers as improper fractions when possible, rather than mixed numbers. So please don't write not 3.5. So we'd rather not do the mixed number idea. I'm sorry, it wouldn't be 3.5, would it? So not 4.5. All right, so 9/2 is the best answer. 4.5 acceptable, but we have fractions, so leave it in fraction form. It's much more or much easier for us to look at. All right, let's do one more, I guess, with this and see what we can come up with. So let's do -2 r squared s all to the 5th power 3 r to the -1 s cubed squared. All right, and our job will be, as we go through, we want to leave our answers with all positive powers. Okay, just to point out again, we have all of these numbers and variables. I'm putting in that extra 1 there to show that it is raised to the 1st power. So in the first term to the 5th power, I'd have -2 to the 5th, r to the 10th, s to the 5th, and that is being multiplied by 3 squared, r to the -2, and s to the 6th power. -2 to the 5th would be -32, r to the 10th, s to the 5th. I guess I should have, but I didn't. All right, so r to the -2, s to the 6. We want to combine like terms, so -32 times 9, r to the 10th times r to the -2, s to the 5th times s to the 6th. Okay, so let's check out what do we get here. So we'd end up with a negative number. 9 2s 18, carry 1, 9 3s 27, that's 288. We are multiplying, so I need to add 5th power plus 6. And let's look at our final result here. So -288, r to the 8th power, and s to the 11th power. So this would be our final answer. I want you to note that in these cases we had a product. Let's look at an example. Suppose I had say a to the -1 plus a to the, sorry, let's do a different variable, plus b to the -1 all squared. All right, let's work inside the bracket first. Notice this is not going to be a to the -2 and b to the -2. There is no rule for the sum. Okay, so there is no automatic rule with indices for the sum, so get that one out of your mind. All right, what could we do? Using our order of operation, we work inside brackets first. This is the same as 1 over a plus 1 over b all squared. If you wish, you can form the common denominator ab, and this is b plus a all squared. So based on what we did with the general power rule, this is b plus a squared in the numerator and ab all squared. The denominator, sure, I can work something out, but b plus a all squared, this will be a binomial, which we'll be doing the binomial expansion and so on later. So this is one way that you can get your answer, or later on we can expand the numerator. But I'm getting a little ahead of myself. So hopefully in this lecture we will get to remembering some of our binomials. Okay. All right, on the flip side, there is one rule of indices that I didn't mention yet. And that was when we're looking at fractional powers. When we're looking at fractional powers, so if I have a to the 1 over n, this is just the nth root of a. Okay. So as we mentioned before, we call this the base on this side, and here is the exponent. When we are referring to these roots, we have a little bit of a different name as we go through. So the root part is called a radical, and of course this here, it's the nth root, and whatever is underneath the root is called the radicand. Now, one of the most common roots that we could deal with is a to the 1/2, which is the square root of a. It is so common that we do not put a little 2, so we don't write a little 2 here. It's just so common that we just drop it. So this is your square root, and oftentimes, because again it's so common, we might refer to it with a different name, which is what we call a surd. Right? A surd, one student asked if surd meant absurd, and no. I believe that in the history of math that the words that were used, normally these square roots and so on, when we left them underneath the square root, they were not solvable, they were not nice integers or rational numbers. And so there were two Arabic words that referred to numbers. The rational ones were, in a certain sense, referred to as soft numbers, or rather, the rational ones were referred to as loud numbers, while these irrational ones were called soft numbers. So it's the Arabic word for soft or soft-spoken that the absurd or surd part comes from, and not from absurd. All right, we have a to the 1/3. This is, of course, the cube root of a. Right. No, there's no other strange word for the cube root of a, and so on. And sometimes we might even have a whole fraction here, a to the m over n. Of course, this could be a to the m times 1 over n, and we look at the notation for each part a bit. This could be a to the 1 over n and raised to the m power. So using the properties of a fraction, and so exactly what we have here is this would be a to the m, and I'm taking the nth root of it, or also equal, I'm taking the nth root of a first, and then raising that to the power of m. Both ways they're equivalent, so but depending on the number that you're dealing with, it could make life a little easier or harder. So if I had, say, 81 to the 3/4, well, if I said to you what is 81 and I cube it and then take this to the 4th, I would need my calculator. But if I did it the opposite way, if I said let's take 81 to the 1/4 power and cube it, well, for those of you who know, the 4th root of 81 is just 3. So this is nothing more than 3 cubed, right? 3 to the 4th is 3 by 3 by 3 by 3, or 9 by 9, which is 81. So I'm using that idea, and taking the 4th root, I end up with 3, and then I cube it, it's 27. So sometimes, depending on what you are given, it might be easier to go one method versus another. All right, as promised, let's look at some distributive property. And we'll also be looking at expansion of some of the binomials. So the distributive property is if I had 3 real numbers, a, b, and c, written in the form as shown, so we're having multiplication and addition, we could look at this as ab plus ac, where you have taken the term on the outside and multiplied each term on the inside of the bracket. All right, so your typical things, let's say you had 5x cubed, and this is, say, 2x plus 3y, or let's do this, x squared xy. Well, what would I get? Each term is being multiplied by 5x cubed, so 2x squared is multiplied by 5x cubed, and 5x cubed is multiplying 3xy squared. So I end up with 10. Remember your rules of indices. These would add to give me x to the 5. I multiply the coefficients. 5 times 3 is 15. I combine like bases. I end up with x to the 4th and y squared. Right? The next method that we will, we're trying to jog your memory, is what we call the FOIL method. So we're going to have a product of 2 binomials. Right. So a plus b times c plus d. And this method is called FOIL. I'll explain what that means. So first I'll take a times c, and then a times d. So you get something like this. You're exhausting each of the products, plus bc plus bd. If we look closely, this is a product of the first term in each binomial. This is the outer term in each binomial, so a and d, they're the extreme ends. These are the inner terms, and then the last term. Whoops. Okay, so the product of the binomials is, we use the FOIL method, but we have some special binomials that I want you to remember, some special expansions, particularly in the quadratic I will give you some for the cubes, but at this stage I won't burden you with knowing all of those. So the first one that we have is, let's take the perfect squares. Some of you know this already, but let me just remind you. If I should write this out and then apply the FOIL method, I would get a squared plus ab plus ba plus b squared. These are nothing more than the same term, so I end up getting a plus b all squared is a squared plus 2ab plus b squared. In a similar fashion, if you go back through and you look at taking the difference and squaring it, you'll get it looks almost the same, just a change in sign. So these are known as the perfect squares. What I want you to recognize, and we're going to look at a couple practice problems just to jog your memory again, that if we call this the first term and this is the last term, in the given binomial, then in each of these cases we have the first term squared. Don't worry about the signs yet. The pattern is that that middle term is twice the mixed product, and then that last term is squared. Right? So this is the pattern, and we also see that if we have a plus sign here, there's a plus sign. If we have a minus sign, there's a minus sign there. Okay? So let's use this. Let's suppose we were given a question, say 5x plus 2 all squared. Although you could go and write out 2 copies of 5x plus 2 and do your FOIL method, I want you to get in the habit of remembering to use this pattern and say it as you go along. First term squared. First term is 5x. It's a plus sign, so it's a sum, so everybody will be positive. Twice that mixed product. What's the mixed product? It's each term will be present, and it's a last term squared. All right. After a while, you'll get so used to doing this that you will be saying it in your head, but writing the result. Anyway, let's show the steps for now, however. 25x squared, 5 2's 10 times 2, that will be 20x plus 4. So this is the expansion of 5x plus 2 all squared. Right? So bear that in mind. So if I end up having, say, x plus 3 all squared. Same idea. First term squared, 2 times the mixed product, and the last term squared. What is that? That's x squared plus 6x plus 9. All right, so that takes care of the first set. So we've just to look at some of the things that we had learned about binomials. Binomial product is done by FOIL. We have this. Then we have some special products. The first set of special products that we have are the perfect squares, and we see the pattern. I guess I should do one with the negative sign so that we can see what happens. So let's say that we had 2x minus 5 all squared. Same thing is true. You can keep, if I'm using the difference, that formula that's at the top of your board right now, 2x squared, put in a minus sign, 2, first term was 2x, last term is 5, and the last term squared. So we'd have 5 squared. Let us expand. We end up with 4x squared. Again, remember your power rule. Each of these were to the first power, so do not give me 2x squared. So if we continue, 4x squared minus 4 times 5 is 20x. And plus 25. All right, so if you have any problems, just check your textbook. There's lots of practice in the review section, and you can try that. All right, the next special binomial that I want to talk about, and you can tell me what you remember it is called. So if I have a minus b and a plus b, then we end up, even if we did the FOIL method, we end up with the only two terms surviving is a squared minus b squared. All right. Yes, that's correct. Most of you remember that this is the difference of two squares. And as I go through my lectures, you'll typically see me write this dots. What do you know? So how would I say this? Do I just say a minus b, a plus b equal difference of square? How would I verbalize what I have here? Right, so remember that equal sign is just is equal to, what would I say on this side? If you recall, this is the product of the conjugates. Product of the conjugates is the difference of two squares. What is a conjugate? So if I have the expression, let's look at, so the conjugate of, say, x minus 5 would be the same terms but opposite sign in the middle, x plus 5, and vice versa. Right? If I go and continue, we had, say, one of these up here, 5x plus 2. Its conjugate is 5x minus 2, and so on. The conjugate of, feel a little squash there. If I should change things and write negative 3x plus 2, if I don't want to rewrite the order or anything, then its conjugate is minus 3x minus 2. Okay? All right. So we have a bit of review there. Let us look at some examples again. If I should have, let's even use the examples we have. X minus 5, and the product of it with its conjugate would be first term squared and the difference of between the first term and the last term. So this would result in x squared minus 25. Let's look at the next one. If I have 5x plus 2 and 5x plus, and 5x minus 2, had it been plus 2, then that would have been a perfect square. So 5x minus 2 would be first term 5x all squared minus 2 all squared, which gives me 25x squared minus 4. Okay. All right. I will just give you some cubics that I want you to know. I won't stress them right now, but they'll come up later on. If we have the sum of cubes in the binomials, so sum of cubes, sum of, the sum. So if I have a plus b all to the third power, the pattern again will be a cube, 3a squared b, 3a b squared plus b cubed. Let's prove this actually. before I write the next one. So we could write this as a plus b times a plus b all squared. We know the perfect square already. This is a plus b, first term squared, 2 times the mixed product, and the last term squared for that perfect square. Now in this case, each term, let's multiply. So let's use the distributive property. And we'll multiply each term by a, and then afterward each term in the bracket by b. So what do we have? When we multiply it by a, we end up with a cube 2a squared b plus ab squared. Now let's multiply throughout by b, and if we do that, we have ba squared. I will just make my life easier. It'll be plus ba squared, which I've turned in the order, and you might notice this is a trick that you can use rather than hunt and peck and searching for everything in one line. Sometimes it's nice to put things in a vertical form under each other, like terms under each other. So b times a squared, we've gotten that. B times the next term, the middle term, would be 2ab squared, and then with the last term it would be b cubed. Let's add everything together, and what do we end up with? Well, we have a cube. We have a cube. Like terms here, these are like terms which I'll combine. Those are like terms which I'll combine. And so I end up with exactly what we had at the top. Right? So some of the pattern, if you're trying to remember this, is that the coefficients are 1, 3, 3, 1. We will again look at this in more detail towards or much later in the course. And you see that the powers of A, so pattern, right, the powers of A are decreasing while the powers of B are increasing. Right? All the powers, all the terms, the power on each term sums to 3. So if you don't see that, so this is what we will call the degree is 3. The degree here is 2 on the A, 1 on the B, so a total of 3. The degree on this term is 1 plus 2. Remember, A to the first is 3. Only B is present here, so the degree is 3. So all the terms have degree 3, and we are seeing this pattern. Okay, let's use it just for one example. I won't make it too difficult, not too high a number. So let's just do, say, 2a plus 1 all to the third power. What would we get? Let's not do a. Some of you get confused. All right, so what I'm doing is everywhere there was a, I'm putting in 2x. So it's the first term cube, then 3 times the first term squared, and then last term. 3 times that first term to the first power, second term to the second power, and that second term cube. Simplifying, 2 to the third is 8x cubed. 4 times 3 is 12x squared. How did I get 4? Right? 2 squared is 4x squared. 4x squared times 30 is 12x. Continuing on, we have 6x plus 1. So we end up with a polynomial, degree 3 polynomial, right? And again, as I mentioned, I'm just giving you, so I've given you this one, a plus b all cube is a cube, 3a squared b, 3ab squared plus b cubed. If we look at the difference, then it's quite similar. We end up with same pattern in the terms, but the signs are going to alternate. Right, and this is what we will have. So bear that in mind. Again, there are a few in your textbook that you may want to practice.